Good day, everyone. Welcome to the 5th session of ARCS Forward and the National Scholar Speaker Series. It's so nice to see so many faces. Thank you all for being here. Today, our topic is machine learning and algorithms. We are featuring 3 ARCS scholars: Jadie Adams from the ARCS Utah chapter, Nick Heller from the ARCS Minnesota chapter, and Biraj Pandey from the ARCS Seattle chapter. We're excited to have them here. I'm Rebecca McNeilly. I'm a member of the ARCS Metro Washington, D.C. chapter. And like many attendees on our webinar today, I have a passion for advancing science in America through the support of our universities and scholars. Personally, I've spent a significant portion of my career in the medtech space with both home diagnostic monitoring and remote patient management technologies. Within cardiology as well as ophthalmology, we leverage AI on our platforms and various algorithms. So it's a perfect topic for me, and I'm thrilled to be hosting today's session. I also just personally work for a LiveCore currently, and we make the personal EKG. And it does, in similar concept, it uses AI to detect, track, and manage heart-related diseases. So ARCS Forward is a relatively new initiative of the ARCS Foundation. Our first session was in May 2021. We established the ARCS Forward National Scholar Speaker Series to inform our audience about science topics that are relevant and interesting to both science and non-science people. By harnessing talent from across the ARCS Foundation network, we've been able to bring together scholars from various ARCS chapters who are researching and working in similar areas of study to share ideas and inform us about their work. Past sessions on prostate cancer, the environment, and public health were well attended and informative. In case you don't know, ARCS stands for Achievement Rewards for College Scientists. The mission of the ARCS Foundation is to advance science in the United States by providing financial awards to academically outstanding US citizens studying to complete degrees in science, technology, engineering, and medical research. For more information about the ARCS Foundation, please check out arcsfoundation.org. On behalf of the ARCS Forward Committee, thank you for joining us today. Whether you are new to ARCS or a longtime member and supporter, I'm glad you are here with us today. As you listen to these speakers, feel free to enter your questions in the chat. There'll be a Q&A session at the end. And if you look at the chat feature, you'll see it on Zoom. That's where you type in your questions into the chat section. So before I begin, I would like to thank our scholars for giving their time here today. And so without further ado, let's get started. We will hear from Biraj Pandey representing the ARCS Seattle chapter.
Awesome, thank you so much. Let me share my screen real quick. Okay. Everything is visible, yeah? Things are good? Okay, awesome. So let me get started. So thank you so much for giving me the opportunity to talk to you and listening to me. So I will kick off this ARCS Forward event on ML and algorithms by sort of giving you a gentle introduction to these ideas, right? So this will probably be fairly non-technical. So if you were expecting a lot of math, too bad, right? So okay, let's get started. So I'm a 4th-year PhD at the at University of Washington in applied mathematics, and so let's begin. And I think, for me, I like talks to be sort of interactive, right? So if you have any questions, just like type in the chat. I think I sort of structured it so that we do have some time to answer questions in the middle as well. So please just let me know. Okay. So, so these days, right? So we talk about machine learning, we talk about algorithms. It's like the rage these days, right? So I figured, first let's start very basic. Like, what is an algorithm, right? Like, what does this thing even mean in the first place, right? So here's a definition I got from Webster, right? So it's a set of very well-defined steps that are followed in order to solve a mathematical problem. All right, so again, you have a problem you want to solve. And so an algorithm just tells you a set of very well-defined steps, and you follow them and then you solve it. All right, so a very concrete example. I give you a list of numbers. All right, so here there are like 5 numbers, right? And I tell you, okay, what is the largest number in this list? All right, so now, well, for you, you probably just saw this and figured it out in like a second, right? So, but if you had to do this systematically, you could say, okay, well, I'm going to start from the left, and I'm going to keep track of the largest thing that I've seen so far. So, okay, right now it's a 0. Then I'm going to compare it to the number on the right, which is a 4. Is 0 bigger than 4? Not at all. So, okay, 4 is my next biggest number, right? And so you keep on doing this until you encounter 10, right? And then 10 is going to be, so it's going to be your largest number. Then you compare it to the thing on its right, which is a 9, and you're going to see, oh, 10 is still bigger, and you're going to keep doing this. Okay, so but the answer is 10, right? Okay. So now, if you had to explain this to a computer, right? So you would give it an algorithm. So here's the algorithm that so written in a more formal way. All right. So the algorithm, it solves this problem, finding the largest number in a list. Right. I call it largest number. The algorithm name, the input it's gonna take in this list of numbers, and then it's gonna give me the largest number in the list L. And here's sort of the steps. Right. It doesn't matter if you didn't understand the algorithm, but the point is, it's the set of steps. Right. And so you might think, okay, if you don't do mathematics professionally or computer science professionally, you might think, okay, I don't know about algorithms, but actually you probably do, right? So here's a very simple algorithm. So it was Valentine's Day yesterday, so I kept it topical, right? So here's an algorithm to bake Valentine's Day cookies, right? So, here's a very large algorithm, but your mathematical problem is to bake your loveliest Valentine's Day cookies, right? My inputs are going to be flour, right? Baking powder, salt, butter, sugar, egg, vanilla, right? Output is going to be cookies, and here's sort of how you do it, and bam, you get cookies, right? So, so you probably have experience with algorithms in your day-to-day life, right? Great. So hopefully that was clear, right? Sort of like this intuition behind algorithms and what they mean, just a set of steps. So now let's go on to the second part of this forward event, which is machine learning, right? So what does it mean, right, for a machine to learn, right? And I think this is actually probably a very philosophical question, right? Because learning involves a lot of things, right? It involves being able to solve your math homework, but also practicing tennis and being good at it, or learning the directions to place, right? So learning means actually a lot of things. How do you actually make this idea concrete? And actually, computer scientists and mathematicians have thought about this for a very long time, and so they sort of broke down learning into a few categories. I'll give you a few, right? So learning could mean classifying things, right? Which means I give you some pictures, right? I give you some pictures of a cat, pictures of a dog, and then from these pictures, right, you were able to tell me that it is a cat. You sort of know what makes a cat, the cattiness or the dogginess of a dog. You're able to recognize it, and you're able to sort of recognize the contents of an image, right? So that is one sort of learning task, right? Something like a concrete idea that means to learn, right? The other things could be learning how to group similar things, right? So which means let's say I give you some songs, right? And I give you the music of these songs, right? And then I give you like Passion Fruit or Don't Let Me Down or Jailhouse Rock and whatever. I give you these songs, and then you're able to sort of listen to the music. I don't tell you who sang that song, whatever. I just give you the music, and sort of this algorithm, right? You're able to sort of classify these things, saying, oh, Hey Jude, Let It Be, and Don't Let Me Down were sung by the Beatles, so they sound probably similar, versus these ones by Elvis, and then these ones by Drake, right? So you sort of know how to sort of categorize things, right? Intuitively, you use some rule that to categorize, to group similar things together. And finally, right, another category is to predict things, right? Here's an example of sort of trying to predict house prices, right? I give you features of a house, right? Which means, let's say, for a given house, its area, the number of rooms that it has, and its zip code. And then using some algorithm, right, or use some set of rules, you try to find the price of the house, right? So a 2,000 square feet house with 4 rooms in the zip code 76039 costs $400,000, right? Whereas you know, a 1,600 square feet house you know, with 4 rooms in the zip code 9105 costs 1.5 million, right? So you know, so I give you these examples, right? You see these listings, and then you try to predict for 1,500 square feet house with 3 rooms in this zip code, how much is it going to cost, right? So these are sort of 3 sort of ideas of what it means to sort of learn, right? Is that clear so far? Any questions? Hopefully it was fairly concrete. I'm just gonna take a swig of water. Okay. So now let's actually do one of these things, right? Let's actually, let me give you an introduction to your first machine learning algorithm, right? Okay, let's learn this, right? So here's a very simple task to predict things, right? Let's learn to predict some house prices in Seattle, right? Again, these numbers are totally fake, by the way. I know nothing about the housing market, but I just wanted to give you a very concrete example. Okay, so here's sort of your data, right? I tell you, okay, a 500 square feet house costs $100,000. 1,000 square feet house costs $200,000. 3,000 square feet house costs $600,000, right? And so on and so forth, right? So I give you these listings, right? So again, your goal right now is I give you the area and you try to predict the price, right? So given these listings, can you tell me how much would a 4,000 square feet house cost, right? Just stare at it, see if you can get it. I'll give you like a few seconds, right? See if you can figure this out. Yeah, put it in the chat if you have any guesses. Oh, there. Okay. Okay. There we go. Okay. There we go. Nice. Okay. There we go. So okay. I see a lot of correct answers. Exactly. Exactly. So you did figure it out, right? You sort of stared at it and you figured out house price is basically 200 times the area, right? Your price in math form, your price is 200 times the area of the house. And so here's your first machine learning model, right? I give you the square feet, right? And you're able to basically predict the price, right? There we go. So very first ML model. Great job. Amazing, right? So now let's look at a little harder example, right? Like maybe this is how you'd actually expect real listings to look like, right? They're not going to be as nice numbers, right? So, you know, 500 square feet house costs $239,000, right? And then whatever, right? Look at these numbers, right? And you stare at it, and I would be very surprised if you could actually predict this accurately, right? This is like kind of difficult. Maybe the only thing you see here is, okay, at least one thing that does make intuitive sense is that the larger the house, the more the price, right? Okay, at least hopefully that makes sense. Okay, so how would you solve this, right? So maybe you stare at this for a minute, and then you go back to your high school algebra class, and you say, okay, well, let's graph this, right? Let's look at this in a graph, right? Okay, so here's a graph. To remind you, the way you sort of graph, you know, your data is on the x-axis, right? So this is your x-axis. This is your dependent variable. So this is your area. So you're looking at the area here, and then on the y-axis, it's your price, right? In dollars. And so what you do is you say, okay, for 500 square feet, which is around here, so between 0 and 1,000, this is my 500. It's going to be $239,000, so somewhere around here, right? And similarly, right? So for 6,000, right, which is like somewhere around here, it's going to be, about like $100,000 around here. So you plot this, and you look at this, and then you see, oh, okay, this looks like a line. Okay, you take your ruler, you draw a line through it, right? And there you go, right? Like, okay, now, you probably will do a fairly decent job at predicting, right? To find the price of a 4,000 square feet house, you look here, you look at 4,000, and then you look at its corresponding Y value, bam, it's about $600,000, right? So there you go. Another, so you're another machine learning algorithm, right? You just draw a line through it and predict, right? And just read off the numbers, right? And this idea of fitting a line, right? It's called linear regression, right? So this is actually a probably one of the simplest things you can do in machine learning, right? And it's simple, but it doesn't mean that, it's stupid or anything. It's actually fairly profound. And a lot of I think the basis of modern machine learning is actually based on this idea of just fitting a line, right? And there's an algorithm to do this, right? An algorithm, so fitting a line to my data, right? It takes its input A, list of house area, its output H, and it returns the slope and the intercept. So if you remember your high school algebra, a line is defined by a slope and intercept. So you do this mathematical operation and it returns the slope and the intercept, right? And it does it in some optimal sense, right? It fits sort of the best possible line you can ever fit to this data. And if you did this, here's the rule, right? Your price is going to be 101 times your area plus sort of this intercept, right? Plus this $224,000. So there you go. So this is one of the simplest ML algorithms that you could ever do. Does this make sense? Does anyone have questions? Another swig of water. Okay, if not, now, you could have done this in the previous example, right? Where things were sort of linear, right? The relationship between your input and your output were just defined by a line. But when these relationships between they get sort of complicated, we're going to need more heavy duty models, right? And so what does it mean for your relationship to get complicated? Maybe something like this. So something very highly nonlinear relationships, which means, let's say, I'm showing the same thing, right? So on the x-axis, it's your area, right? How big your house is, and the y-axis, it's price. Now, let's say for whatever reason, right, it looks very cyclical. People really love a 500 square feet house, and it's quite high, but then they don't really like a 1,000 square feet house for whatever reason, right? And so if this is your data and you try to fit a line through it, you're probably going to make a lot of error, right? So for a 3,000 square feet house, you're going to say it's around $600,000, even though in reality it's more closer to $400,000. So a $200,000 a mistake, right? So so you're going to sort of need things that can understand these more complicated cyclical type relationships, right? So fitting a line is not going to be enough. And then similarly, computer vision, which means, again, this idea of recognizing images, right? How do you even go from this idea of here's a picture that has some object in it, right? And you have some this intuition about this object. You sort of know what a cat ears look like, right? You have this image in your head, but how do you define these preset, these set of rules that go from your, these abstract ideas of a cat to so that you can use those to actually classify this picture, right? It's a very hard problem. So you're going to need more heavy duty models, like neural networks and whatever. And so, these days, modern machine learning algorithms, right? So they can easily find patterns from data, right? So they're sort of this, the Swiss Army knife, in a sense, in that, a similar model can predict things. It can learn how to predict house prices, but it can also learn how to predict, recognize pictures of a cat. And help you to find the shortest path from your house to your grocery store. So they're very flexible, right? That's why they're so powerful these days, and you can leverage them to do lots of really cool applications. And the way you sort of do it, right? Sort of this idea is going to be, you have some algorithm, right? You give it some training examples, right? So you give it something to learn from, pictures of cats and dogs with correct labels, right? And then it sort of learns from these pictures what makes a cat as it sort of trains. But this idea of training itself is a very abstract idea. It's not, it's tough to sort of explain to you what it means that this thing trains. It's sort of not, the way an algorithm trains is not sort of what you think, when you think about training. And sort of it looks at a lot of these images, right? And it sort of learns, right? Given some mathematical rules, it sort of learns how to predict going from a picture to its label, right? But unfortunately, right, to distill what this algorithm is learning, right, to intuitive rules sort of remains a challenge. And that's why oftentimes, if you ever read machine learning articles in Scientific American or Quanta or whatever, you often hear phrases machine learning is a black box, or it still remains a mystery and things like that. Sort of a satisfying explanation is we still don't have it, but they work really well in practice, and that's why they're sort of the rage these days. And so, okay, let me tell you a little bit about my work. So my work actually lies at the intersection of machine learning and neuroscience, right? So I investigate questions like, what are the mathematical properties of machine learning algorithms, right? So I don't really focus on the use cases, but sort of analyzing things that do work well. So, when should you stop training an algorithm, right? Like, if you know that something trains really well, how well is it going to test, right? Or how many examples is it going to need to achieve a certain level of performance, right? And on the flip side, on the more neuroscience aspect of things, like, a machine learning algorithm can differentiate between cats and dogs, but so can the brain. So, what are the similarities between how the brain learns, how you and I learn, versus how these artificial algorithms learn, right? What are the differences? And so so these are sort of the questions that I sort of investigate. Okay, so let me summarize because I'm definitely out of time. So, okay, what did I say today, right? So algorithms are well-defined steps to solve a mathematical problem, right? Think about baking the cake. And then some machine learning algorithms can classify things, they can group similar things together and predict things. And we went through an example of learning how to predict house prices. And we saw this idea of fitting a line, right? But when relationships, when they get complicated, you're going to need more complex models, right? And then finally, despite their practical success of satisfying a good explanation of why these modern machine learning algorithms work, they sort of remain elusive. So that is all I have to say. So hopefully you learned something. And yeah, thank you so much for listening to me.
Biraj, this was great. Does anyone have any questions before we continue? Received kudos, great explanations.
I see. Awesome.
During the Q&A, if there are any more questions for Biraj, we will tackle that at that time.
Absolutely, yeah.
Great. So we will move on to our second presenter. And what I'd like Jadie to do is Jadie Adams from ARCS Utah, who's an ARCS Utah scholar, will take over as our next presenter.
Great, thank you, Rebecca. Hopefully you guys can see the slides. And thanks, Biraj, for your presentation. I think that background will be really helpful in understanding mine. So I'm a student at the Scientific Computing and Imaging Institute at the University of Utah. And I'm working towards a computing degree in image analysis, and I'm part of the Utah ARCS chapter. So my background is in statistics and modeling. I'm a mathematician at heart, but I've become really interested in machine learning. I previously worked in deep learning for automatic speech recognition, and now I've pivoted to computer vision, specifically statistical shape modeling from medical images. So I'm going to be talking about this application of machine learning, and that's learning a statistical shape model. So statistical shape modeling, or SSM, is a technique for capturing and measuring shapes in relation to a population of shapes. So as an example, here we have some examples of different femur meshes from the femur bone from different patients. And so SSM allows us to compare these femurs to each other and quantify where and how they differ. Oops. Yeah. So this is a useful tool in medical image analysis where we have bones or organs that are segmented or delineated from 3D medical images such as CT or MRI scans. Once we have this shape, we can build a shape model, which then can be used to quantify variation in the population or used to solve medical questions related to detecting disease or diagnosing pathology. So for an example here, an orthopedic surgeon might notice that people who are having hip pain have a wider femoral neck. And so a shape model could be used to verify and quantify that hypothesis. So now that's the motivation for SSM. And now I'll go into what it entails. So the first thing we need to talk about is what we define shape as. And so in this context, shape is the characteristics that remain once you remove global geometric information. So this includes location, orientation, and in some cases, size. So we're interested in the differences that remain once we remove these factors. So here in this example, you can see that's what's circled in. And so what SSM is capturing is what we call shape parameters. So for example, if you consider an ellipse or an oval, we can completely characterize the shape using the minor and major radius. And so that's an example of a shape with known parameters. But typically what we're interested in is shapes where we don't know the parameters. So for example, dogs. And so we're interested in how we can learn these. This is another example on the right here of shapes with known parameters. You can see these sliders here are controlling this group of shapes called super shapes. And we can completely characterize the shapes given the values of these sliders. So when you think about learning SSM, what the model's trying to learn is essentially these slider values. And so how we do that is, well, this is one technique for doing that, and that's using landmark points. So landmark points are just points on the shape that are in correspondence across the population. So you can see in this hand example, we placed a point on each fingertip and those points correspond across hands. So it's a way of characterizing shapes. And so what we're interested in doing is automatically placing these landmark points. And so this brings me to ShapeWorks, which is an open source software tool that I'm helping develop at the University of Utah. And what ShapeWorks does is it automatically places a dense set of these landmark or correspondence points across an input of a group of shapes. And so you can see by the color pattern here that these points on the shape are in correspondence across these two different femurs. So they're used to characterize the shape. And so this is an overview of how ShapeWorks works. And it's kind of this big pipeline where you start with an input shape, such as a mesh or a binary image where we have the shape labeled. And then the first step is to groom them. And this is pre-processing that essentially removes that information I showed before, such as location, orientation, and size, so that all of the shapes are in alignment. And then once we have that, we optimize point positions on those shapes to get our landmark points. And then once we have those sets of correspondence points, we analyze them and visualize them so that we can see how the shapes vary across the population. So now I'll go into each of those steps in a little more detail. Here's an example of grooming or pre-processing. So imagine you have these femur meshes on the left here, and you can see some of them are left femurs and some are right. And so we'd want to pick a side to reflect so that we can compare across both left and right. And then we also have different shaft lengths in the femurs here. So when the shape was selected out of the image, it was selected ending at different points. So we might want to clip those so that they all end at a uniform place. And then the last step would be to align them to each other. And so the output of the grooming would look something like what I have on the right here, where all of the shapes are aligned. And the next step is to place these correspondence points on the shape. And we do this using an algorithm, which essentially solves this optimization equation. And the optimization equation is giving us the best possible correspondence points. And it does that by weighing two things. The first is the entropy or complexity of the overall model. So it's essentially trying to minimize how complex the model is. And what this does is it ensures good correspondence across shapes. And then the second part of the optimization equation is trying to maximize the entropy of the correspondence points within a particular shape. And so this encourages the points to spread out so that they are like uniformly covering the shape and so that they accurately capture it. So this optimization equation is kind of balancing these two competing objectives. And here's what that looks like when we actually run optimization. So you can see the points are moving so that they're spreading out across the shapes, and they're also in correspondence. So if you look at one colored point on one shape, it's in roughly the same location on another. And you can see here on the left, there are all of these parameters which are related to that optimization equation, and those can be tuned to get a better shape model. So once we have our correspondence points on every shape, we typically analyze it by considering the mean shape. So we take those sets of particles or points on every shape and we take the average of them and we get a mean shape. And this example here, this point is just a little reconstruction artifact because it's just creating a mesh using the points alone. But once we have the mean shape, we have kind of a representative femur of our whole population. And then what we can do is we can warp it using the modes of variation within the population so that we can visualize how these shapes vary. So here I've shown the first mode of variation, and you can see it's kind of related to the length of the femoral neck. And so that's kind of an example of analyzing. And here's an example where we know what to expect. So these are 3D ellipses, and they vary in their X radius and Y radius. And you can see that when we visualize it, it correctly captures the X radius as the primary mode of variation and the Y radius as the secondary. And this is a little bit of a trickier example where all of our shapes are ellipses, but they have this cavity. And the only thing that varies across shapes is the location of this cavity or indent in the ellipse. And so looking at this, we can see that the particles or points inside the cavity stay inside of it, and the ones on the outside stay outside. And the only mode of variation that's captured is the location of this cavity. So that's kind of a proof of concept that the model's correctly characterizing the shape. So now I want to talk about some applications, and this is work we've done in collaboration with the orthopedics and cardiac department at the U. This first one, which I've kind of alluded to, is looking at the hip joint and classifying CAM pathology. So if we look at the mean shape of normal or control femurs compared to the mean shape of patients with this CAM pathology, we can see the femoral neck is thicker on the CAM patients, and this can cause hip impingement. And so that's an example of how we could use that shape model. I also have an example. This is the left atrium of the heart from a cardiac MRI scan. And in this work, they used the modes of variation from the shape model to predict whether or not atrial fibrillation would reoccur in patients that had experienced it. And they found that the shape model accurately predicted this. And so, as you can imagine, this would be very useful information. And so now you might be wondering why this isn't a widespread clinical tool. And there's a few reasons for that. The first is that it requires a medical professional, someone with domain knowledge, to take the 3D image, either CT or MRI, and to select that shape from it, because the input is the shape. And then the second is the optimization pipeline is computationally and memory-wise very expensive. And to optimize, we have to tune those parameters I showed, and that can take some expertise as well. It's kind of a steep learning curve. So there are kind of some hurdles to be able to use this in practice. And so deep learning is kind of the direction we're going to make this more feasible. And so deep learning, like Biraj alluded to, that it uses neural networks. And basically, this example, this model, Deep SSM, was originally developed by my lab mate Riddish, and it replaces the ShapeWorks pipeline for predicting a shape descriptor. And so the input is a raw image, an unsegmented 3D scan, and we pass it through a trained neural network, and it predicts the shape. So you can see it kind of replaces these steps on the left here, which is the standard ShapeWorks method. In order to get this trained network, however, we need training data, and to acquire that, we use the typical ShapeWorks pipeline to get some correspondence points for the training data. So here's kind of an overview of the network. So the input, again, is a 3D image where we haven't pre-selected the shape. It's just the raw image. And then we pass it through what's called a convolutional neural network. And this is what Biraj referred to as the black box, but essentially it's just kind of a big math equation of multiplying by weights and adding bias terms to get an output. And then we get an output, which is just a long string of numbers, and we can reconstruct that into the correspondence points. So this is kind of an end-to-end model, and we train it on examples where we have the 3D image and the correspondence points, so we know what the target is. And then when we test it, we just pass through the 3D image and we get correspondence points. So here's some examples of results. I have some slices of the 3D images here, as well as a mesh of the predicted shape. And then in red on the 3D image is kind of where that predicted shape lies in the image. And so we found that DeepSSM has similar accuracy to the typical pipeline, and it can be used for making downstream predictions with equal accuracy to ShapeWorks. So this is really great news because it cuts out kind of all of the prohibitive steps of shape modeling, but we can't just incorporate it into on-site clinical tools. And the reason for that is because, like Biraj mentioned, deep models are kind of black boxes. We don't know exactly why they're making the predictions they make. And so we can't just trust their predictions to use in like sensitive clinical decision making. And so one step we can take towards making this more usable is to add estimates of model confidence or uncertainty measures. So this basically says the model will output a prediction as well as a measure of how sure it is. And there's two kinds of uncertainty that come up when we're talking about these models. The first is data dependent. So that's uncertainty inherent in the input data. So for example, maybe the scan is overexposed, or it has noise, or there's a lack of image features that are indicative of shape. And the second is model dependent uncertainty. And so this accounts for uncertainty in the model parameters, and it can be explained away given enough training data. So if we had enough representative data, the model could learn and have no uncertainty, but that's never typically the case. We never have enough training data, and so there's some uncertainty within the model. And this brings me to my work, which is DeepSSM with uncertainty quantification. So this is a Bayesian extension of the network, which means that it produces probabilistic predictions. And so essentially, we have the same input, an unsegmented image, and the same output, a shape model, but we also get granular estimates of both forms of uncertainty. And so the way this is done is we adapt the model to, instead of just predicting the correspondence points, it predicts mean and variance of the correspondence points. And the variance tells us how sure the model is about each point's location. And then to adapt it for epistemic uncertainty, we have it predicted distribution over model parameters by adding dropout to the network, which essentially is just turning on and off network weights. And in that way, we get a distribution of predictions, and we can use that to know how sure the model is. So here's some example output where you can see that the error encoded as a heat map kind of overlaps with the model uncertainty, which is higher where it's red, and that is kind of the pulmonary veins of the left atrium, which vary a lot. So as we'd expect, the model is less sure about those veins. So that's kind of my work, and in future work, I'm trying to compare other methods and improve upon them for predicting uncertainty. And I'm also working to adapt that ShapeWorks optimization equation to be able to predict shape models from 4D data. So that's 3D shape plus time. Think about like a scan of the heart throughout the cardiac cycle, or a CT scan of a bone before surgery, after, and 3 months after. So there's a lot of medical questions that involve time, and extending ShapeWorks to be able to handle that would open the door for a lot of questions. And then after that, I intend to explore deep learning frameworks for 4D SSM as well. And so to wrap up, I just wanted to talk about the potential I see for this work and why I think it's important. I think SSM is a tool that can really improve medical standards, and deep learning can see way more examples than a human could ever look at. And so there's a potential for better than human accuracy in diagnosing disease and detecting pathology. And the deep learning pipeline also greatly reduces the kind of expert-driven steps, the manual steps, and the time required. So this would lower costs and make this kind of prediction more accessible for patients. And adding uncertainty quantification will provide the safeguard necessary to make it more feasible to use these tools in a medical setting. That's it. I just want to thank my advisor, as well as the ShapeWorks team, which is comprised of professors, students, and software developers. And I also want to thank ARCS for supporting me in this research. Not only is the funding very helpful, but also the community has been really beneficial for me, and I appreciate the network ARCS provides. So thanks.
Jadie, that was fabulous. Just such important work. We do have 2 questions for you, if you don't mind me asking while we're here. Can you provide examples of how SSM is used in diagnoses?
Yes. So we consider diagnosing disease as a downstream task. So it's kind of funny because we're building a model of shape, and then we can use that model of shape to build a model that predicts disease using the shape parameters. So essentially, it's the input to another model that then predicts disease. So if you have scans of shapes and you know the diagnosis of a disease, you can create training data from that, and then you can train a model based on that to diagnose the disease. Does that make sense?
Yes, perfect. And we do have another question for you, but what I'll do is let's go forward because I don't want to run out of time. We'll have Nick present, and then we'll circle back for, we have 3 more questions for you guys. So without further ado, I would like to introduce Nick Heller, and he is from the ARCS Minnesota chapter. And without further ado, please take the floor.
Great. Everyone can hear me. Everyone can see my screen. Hopefully take that silence as a yes.
Yes, we can see your screen.
Great. Okay. So thank you for the introduction, and thanks for the invitation to speak. As you said, my name is Nick Heller. I'm a PhD candidate at the University of Minnesota in my 5th year. And I'm going to be talking about something really related to the great presentation that Jadie just gave, which is semantic segmentation of cross-sectional imaging, which is, it kind of produces an input to the software that they're producing over in Utah. And I'll be talking about an application to renal cancer. So I'll start with just like a quick background on that. So renal cancer is cancer of the kidney. There's an estimated 74,000 new cases and 15,000 deaths in the US alone this year. And it's kind of an interesting disease where it's really not treatable once it becomes metastatic. It's one of those that there just hasn't been a ton of progress on the metastatic version, but when it's still localized, surgery is often curative. They can actually go in, as long as they get all of it, when they take it out, it won't come back, or it usually doesn't come back. So it's really a great opportunity for surgery to shine in kind of curing cancer. So we want to do everything we can to support surgeons in kind of going in and getting these. And a little bit of background on semantic segmentation applied to this problem. That is kind of the question of, you get a cross-sectional image which has voxels, right? It's kind of the 3D version of pixels. And for every one of those voxels, you're trying to make a decision about what it belongs to. So in our case, we were interested in the kidney, which is kind of showed in purple here. the tumor, which is shown in green, and any cysts that the kidney might have, which is just kind of pockets of fluid that are not harmful, but look kind of like tumors, so we're interested in getting them. And once you've done that on every slice or every voxel of an image, you can produce these 3D models, right, that look a lot like statistical shape models that Jadie was just talking about. And she had great examples of why these things are useful and why they're kind of becoming a really important part of clinical practice. So what I'm going to be talking a lot about is the deep learning models that we use to go from that image to these models. And what we do is we use convolutional neural networks. And this is kind of a diagram that shows a simplified version of one that's often used for medical image semantic segmentation, which is called the UNet, which you don't have to understand everything about every operation that's going on here, but you can kind of think of it as like the linear regression steps happening on each pixel in different scales. So in the beginning, we kind of have this skinny and wide thing. That's kind of the input image. And we have a lot of these regression type problems going on and being solved. And then we downsample with various types of pooling, or we call them strided convolutions, which kind of allow us to integrate information in the spatial dimension into something that considers things more globally. And you keep doing that down to a low level where you have something that's very low spatial resolution, but has a lot of detail, a lot of features, we say. So it's kind of, it's narrow but deep. And then we start heading back up. So we incorporate that information that we created or we learned at the high spatial resolution, low depth. We kind of copy it back over, but then we're also taking that information that we considered globally and kind of propagating it back up. So it turns out to be, a fairly complicated model. There's a lot of operations going on. And, this didn't fall out of the sky, right? This is something that someone created, someone invented, and they made some decisions in doing that. And the number of decisions that you have to make when you create a neural network is just enormous. There's so many degrees of freedom when you're doing this design. And not only that, but also how you train it. What data do you show it and when? How big of a batch size you show it? How many images at once? How do you optimize it, right? What kind of steps do you take based on what you know about what it predicted versus what you wanted it to predict? So there's a ton of design decisions, and because these things are so expensive to train and to run, it's hard to say what really works, because you can't try everything on every data set, and the data sets that are out there, especially in medical imaging, are not very big and fairly scarce to begin with. So there's a lot of uncertainty, a lot of debate in the research community about what really works and what we should be focusing our attention on in machine learning. And so there's these things called machine learning challenges, which I really like. And I think they provide a lot of clarity to the machine learning community about what really works and why. And that's really the research project that I'm going to be telling you about today, is one of these challenges that I hosted. So what you have when you have a machine learning challenge is, first, an interdisciplinary group builds a data set, right? Which is kind of these images with those corresponding labels. You have some clinicians go in, they look at the images, and they give you a 3D model of, basically, this is what I would say if I were the perfect deep neural network. This is the 3D representation of the kidney and tumor and cyst in our case. And you try to collect as many of these as possible. It's a really hard thing to do because it takes a lot of time and clinicians are very busy. But once you have it, you can then use it to train deep learning models. So these things turn out to be very valuable. So what you do then is you give that data set away. You find the right permissions and you do everything you can to anonymize the data set, and you release it on a website to the greater research community. You just give a download link to anyone who wants it. They can download it and train their model. Basically use whatever the best model they think exists and go nuts, right? So around the world, research teams will download your data and they'll take whatever approach they think is best and train a model. And then they send those models to us as the organizing committee, and they say, rank us, right? Run this model on data it's never seen before. Come up with a number which basically describes how well it's performing, and put us on a leaderboard versus all the other people in the world. And the people who compete are very confident, right? They think what they have is the best. So they want to see themselves at the top of the leaderboard. So it's kind of these fun little events, right? Where if you do this, you can provide a lot of clarity to the community, because everyone's being evaluated on the same data set in exactly the same way by a centralized committee. And they've turned out to be a really kind of important part of the machine learning community at various conferences. You know, they have special events for these challenges, and they're a lot of fun. So why do we do these, right? They provide a lot of clarity, and I kind of just went over this. So ImageNet is one example that people talk about a lot. It's not in medical imaging, but it's just kind of looking at natural images of the world around us, kind of images you would take with your smartphone, and you try to classify them as belonging to any one of 1,000 different classes. And I think a few hundred of those classes in ImageNet were actually dog breeds. So you kind of have this combination of really fine classes. You know, it's very difficult to tell different dog breeds apart versus, you know, a dog breed versus a sailboat, right? You know, it's kind of a wide range. And that challenge happened, I think, you know, started around 2007 and went for half a decade or so. And it really revolutionized the field. It saw kind of the turn of the century for medical or for deep learning. You know, the deep learning kind of came into its own towards the end of ImageNet, and ImageNet is really what proved it. It showed that deep learning is really the approach that we should focus on because it won ImageNet. So in medical imaging, it wasn't long before, you know, we were doing these challenges too, and really saw the benefits that they could provide because of how scarce our data sets are and how valuable they are once they're created. So there's some examples of popular data sets on the right there. So the challenge that I'm going to be talking about is called KITS-19. KITS stands for kidney tumor segmentation, and it happened in 2019 in conjunction with MICAI, which is a conference in this space. And basically what we did is we saw, well, there was no data set out there for semantic segmentation of renal tumors. So we set about creating one. We went through all patients that came into our institution, the University of Minnesota Medical Center. We screened them by the procedure code. So we're looking for patients that went to surgery for a suspected renal cancer. And we screened them for, you know, how many of those had imaging available that we could download. And you know, we did a little more screening to make it a little bit simpler for ourselves. We removed cases that the thing that was operated on was actually assist. So we didn't want to confuse the model at that point. And then we randomized it. 70% of it went to a training set, and that's the part that we gave away. We made a download link and let anyone in the world who wanted it get this data. And we kept 90 cases sort of private to ourselves, and those were kind of top secret. Nobody saw them except for us. And that was what we used to evaluate each models and rank everybody. There's a very diverse data set. A lot of times when people release these data sets, they're kind of really standardized, and you have maybe one scanner brand, and everything was created at isotropic spacings and everything. Wasn't the case for us. We were doing this retrospectively, so we had you know, maybe 70 different scanning centers represented, and everyone kind of has their own way. So it's really kind of a natural data set. It's sort of the thing that a model would see if it was applied in the real world, which I think added a lot of value to our challenge because it made the problem harder, right? If things are really standardized, it's easy for a model to learn that. But if you're dealing with real world data, things are messy, and we wanted to capture that. So the data, as expected, was kind of centered around Minnesota. Like I said, these are patients treated at the University of Minnesota, but they were scanned at about 70 different sites, and that's what's being shown on this map over here on the right. So with any competition, you need to have some rules, right? So our rules were everyone had to write a paper about what they did, right? We wanted to make sure that the results of our challenge were known to everybody. We wanted to make sure that if somebody won, it would be clear how to reproduce what they did, because that would obviously enhance the impact. And we didn't allow people to kind of keep submitting. It's kind of this problem in machine learning that if you try enough things, eventually one of them will work, and it may not be that it's actually better. It may just kind of be random chance. It's an unfortunate thing that you can train the same neural network 10 times and you'll have not the same result every time. You'll have kind of a distribution of results. And we didn't want people to be able to just game that and kind of keep submitting the same thing to get the best that they could possibly get. So people were able to submit a few times, but they weren't able to see their result until the end. So that it was only the most recent submission that we actually scored and provided the result for and ranked. I'll skip that. But teams did try to kind of game this system, right? It's kind of a funny thing with these competitions is that they become so important that startups will use them to get funding, right? Startups will have their engineering team come and make submissions, and then they'll go to funders and they'll say, look, we have, you know, a great team of engineers because they were able to win this competition at this conference, right? So there's a lot of motivation for teams to come in and do well, and some actually tried to kind of cheat by making the same or making different team names and competing under different names, but it's actually the same people. And so we had to be kind of on the watch for that. And it's just kind of one of those funny things that you don't think about when you try to organize a research project, that someone might try to cheat, but that was one thing we did have to worry about. But we did have a lot of participation. We had over 100 teams from around the world download our data set and submit a model to us. And we had, I think 5 continents represented, which we were really, really happy with. The conference was actually in China, so there were quite a few competitors from China and Asia as a whole. So it was really a lot of fun to see these models come in and to see, the various communities represented and kind of how vibrant this research community has become. So the top scoring teams did really well. These are dice scores, which is kind of a way to rank a semantic segmentation versus its ground truth. You don't need to know what the absolute numbers mean, but if you compare these to what a human will do if they try to segment the same thing twice, it's actually right on par. So that pink line is for the kidney region and that blue line is for the tumor. And it might be a little bit hard to see through the Zoom, but there's kind of a median line here on the maroon line. And that for the top scoring team was right on with our tumor results from human to human. So you can see that these models, when the top teams work on them, they can be really, really good. And now this is actually a few years old. The most recent work on our data set has well surpassed what humans do against each other. So it really shows the value in deep learning. If you show something enough examples, the model will kind of even generalize through the noise of humans. If the labels you give it even have some noise, it'll learn to ignore that and predict actually the correct thing when it sees new data. So why do we care? Jadie gave some great examples of how semantic segmentations can be used. We had some other ideas for how we could use these things. One was we took these semantic segmentations and sent them to 3D printers. That's what's being shown on the right here. And then we had some surgical trainees and residents at the University of Minnesota actually go on the intuitive Da Vinci system, the robotic surgical system, and try to excise these tumors as though they were practicing a partial nephrectomy on a patient. And they had a lot of fun doing that. And I think there's a little bit of way we still have to come in soft 3D printing. We tried to, make it as realistic as possible, as close to human flesh, but that's a hard thing to do with a 3D printer when you're printing various polymers. But it's something that's making a lot of progress. And I think this is a surgical simulation is a really great area that you can use deep learning for with semantic segmentation. And then on the left, we just kind of have a visualization of what it might look like to segment the renal arteries, the ureter, and the kidneys and tumors, that you could then show to the patient and say, this is exactly where I'm going to cut. And this is actually your anatomy. This isn't just some model that I have on the shelf. This is what's inside you. And this is exactly what I'm going to do. So this is something that we're trying to get into the clinic and actually show patients in the near term. And that's everything I have. I happily take questions and any questions that might be for the other speakers. And thank you.
Nick, this is again another example of just great work. So we do have one question for you. Do you have any comments on models used in predicting, say, like the pandemic or climate change or any other areas that you're looking at?
Yeah, it's funny. Soon after the pandemic really took off, there was a competition very much like KITS in predicting, I think it was, I'm not an expert in this area, but it was something about damage to lung tissue and kind of segmenting that out. And I think they had an extension on that challenge that was predicting survival. And it's another thing where a challenge was just kind of desperately needed, in my opinion, because there was a ton of research coming out using deep learning for COVID. And you couldn't really tell what worked and what didn't, because everyone was working on their own data set and everything was so new. So when a team came out and kind of standardized things and said, here's a big data set, we spent a lot of time collecting it, we're going to give it away, we're going to rank everybody, it just provided a ton of clarity that I think only challenges can do. But yeah, I mean, there's just enormous potential for models like this to have an impact in COVID and other big problems like climate change.
Thanks, Nick. And before we close, Biraj, we have one question for you, if you don't mind. What are the biggest challenges you see in bridging machine learning and neuroscience?
A very profound question, actually. It's a really, really kind of $1 million question, right? I think one thing that sort of Nick said sort of comes to mind. So, when you're doing these, like these especially deep neural networks, right? You have a lot of these parameters that you can tune. There's so many building blocks you can stack together, right, to make it work. But oftentimes, and they work really well in practice, but oftentimes they sort of don't mimic the constraints that is faced by biology, right? Like what that means is, your brain is a mass of tissues, right? It's sort of connected together in a certain way, right? And only nearby neurons can talk to each other, right? Like things that are, things that are really, really far apart on the two side, on the two, let's say, opposite hemispheres of your brain, like they can't talk to each other, right? But with sort of, these like deep neural networks, which are inspired by the brain, these constraints are sort of broken, right? And so like a lot of times, a big challenge in sort of bridging these two ideas is, it's just that there are different objectives between machine learning and neuroscience. Like one is to just get things to work, right? Like without respecting the constraints faced by biology, whereas in the neuroscience, we really do care about that. And so I guess like, there are different sort of objectives, and the fields are sort of moving apart, right? But at the same time, that is not to say that, there aren't similarities as well. I think someone else also asked me this question about, what was it? The similarities between how machine learning works and how the brain works, right? So, despite these like different sort of building blocks, right? You find if you sort of try to analyze, these algorithms, you see that they're sort of, roughly speaking, behaving in the same way that your neurons do, right? Which is kind of really fascinating. Despite these, without having these constraints, right? They are still sort of representing things in a way that your neurons do, your brain sort of understands. And so, it's sort of fascinating, right? So I guess then the question becomes, are these constraints sort of necessary, right? Like, do we need to respect every biological constraint that the brain follows to create an intelligent machine, or we don't, right? So hopefully it's okay. Hopefully I answered some of your questions. I said a lot of things, but hopefully that sort of gave you some insight. So again, architectural differences, design parameters, but still similar, still see similar representations. Yeah.
No, it's great. Thank you. And I would like to close, because I realize we're over time, by saying thank you to Biraj, Jadie, and Nick. We're excited about the work that you're doing. Thank you for continuing to advance science in America and being the great scholars that you are. Thank you for your time today. And for those of you that were able to attend, we appreciate all the questions. Thank you for submitting them. And if we have the ability, we'll do our best to circle back and answer them outside of this meeting. But have a wonderful rest of the day. And thank you for being a part of the ARC Forward webinar. And then just one final note, because we do have an upcoming webinar. Our next session of ARCS Forward will be on May 10th at noon Eastern time, and it's going to focus on neurological diseases. So we will send out a link to the recording for today's session for you to share. You'll also receive a short survey. Please respond to that and let us know if there's a topic of interest to you. Thank you for attending, and we look forward to seeing everybody on May 10th. Have a great rest of your day. Bye.